Continuing on from a week ago, last Thursday, we were talking about centers of gravity and centroids. And recall what we were doing there is we talked about center of gravity. The interest we have for a center of gravity is if we're designing something, if we're using our equilibrium equations, we need to know a magnitude of a force, and we need to know its direction and line of action. So what we were doing in that whole process is just trying to figure out, okay, where would this line of action be? And then where we would, we'll be able to calculate the magnitude at some point in time later. Then what we did was we found that we could do it in what we call a discrete form of finding that centroid, where we were taking composites. Remember, we were taking square areas, round areas, and that sort of thing, and then just combining them all together in the table method there, creating that column there for the area, and then creating a column for the first moments of area in the y direction and the x direction and stuff like that, dividing those first moment of areas by the area, and that gave us the location of that centroid based upon the axis system that we have shown. And of course, all of our little pieces have to refer to that same axis system, otherwise we'll get a really weird answer. What we're going to do today now is look at doing it via integration. So we might end up, as engineers, especially in the mechanical world, you might be developing turbine blades and that sort of thing, where they're actually cutting them at some sort of an equation or something like that. And we don't necessarily have a nice thing that we can put together in terms of a composite. We don't have a cubic or a x to the fourth type model there. So we're going to actually have to do some through integration. Also, in terms of when you take the EIT, I guarantee you there'll be several problems using integration. Now, integration is usually pretty simple. It's not very complicated, so we're not going to be doing dx dy pieces. We'll be generally doing vertical or horizontal pieces. So what we're going to be looking at then is doing this in integration. It'll be in the 5.6 portion of the book there. My pen's getting... So this is what we talked about last Thursday. We basically were able to calculate areas and these first moment of areas. And what we're going to do in the integration is we're going to just confine ourselves to basically vertical or horizontal strips. So we're not going to be doing double integrations and that sort of thing. But what we're attempting to do here then is we have a some sort of a form there, and we've probably been given some sort of an equation that y is going to be some function of fx there. So it might be squared, cubed, whatever. And what we're going to do is then take either a horizontal or vertical strip. In this particular case, we're going to take a vertical strip. Now, when we look at the strip, we'll do a little close-up of this strip. And except for this little top part here, what we're going to do, this is our what we're going to do is chop off that little top there. Oh, and the other point I forgot to make there too is then what we're going to do is make the width of that strip infinitesimal. So we're going to call it dx. And as we make this strip smaller and smaller, what does this look like? Rectangle, right. Do we know where the centroid of a rectangle is? Yeah, right there. So basically, we're going to be able to create first moment of areas using this strip. We're going to be able to use integration by recognizing the fact that our strips are really nothing more than rectangles, whether they're vertical in this particular case or horizontal. And then note the fact that we can calculate the area of that by just simply y times the dx. So y is going to be the height of this. In this particular case, this one comes down to 0 here. So the height of that is going to be y, or that function of x, times the dx, or infinitesimal piece, and that's going to be our area. One thing I forgot to put there is, goes out to some point A there. And where we're going with this then is that if I have this, so dA is basically, I'm going to get the area by integrating the strip across this whole piece here from 0 to A, recognizing the fact that if I can express my y in terms of x, then I end up with an integral that I can work with. I have an fx, so it's going to be x squared, x cubed, something like that, dx. And basically, at that point in time, I go back to my calculus book and say, well, I can figure that one out. And then we'll do the same thing with those first moments of area. And remember, the first moments of area basically have this now moment arm. So we've got this area here, but now we're going to recognize the fact that it's got this moment arm now, and as I move along there, it moves away, so that x is going to increase. And I can resolve it to this by the fact that I note that if my x of c is to the center of this thing here, if I'm considering infinitesimal pieces, then what I'm saying then is my xc basically is going to be that x that I'm using in terms of that infinitesimal small strip there. So I take x and I'm moving it along there. That's my fx up here. So I'm going from 0 to x, and I'm doing an integration across there. All I'm saying here is now in this first moment of area, I'm just simply adding another x there. Because that's infinitesimally small there, the xc will be at the center of that rectangle there, which is also going to be the same as x going through that. That's the easy one. Oh, and then we'll once we get those two pieces there, then we can go ahead and calculate that location of that centroid via integration. Okay, the slightly trickier one is going to be the y direction. It's an ugly looking. And that's what that one looks like. Now the problem is YC.
So that's the same thing that we had originally, right? So
am I doing the wrong one here?
I'm saying like no, not that, but like our center, that's what the x coordinate of the center is, right?
Yeah. So that's the same thing we were doing with the composites. Yeah. Once we get to that part, we've got a first moment of area, and we got the area. We just divide the two, and we'll end up with a length, right?
Yeah.
Okay. So same thing, yes. The only difference is that the way I'm getting there is via an integration now instead of being able to pull it right out of a book. Okay. So same thing. Now, that's a very good point to note there. It's going to be the same thing when I get down to this point, but to get these two pieces, I'm going to have to do some integration.
Okay.
Now, the y direction there is going to be a little bit different there. But again, note that if this is a rectangle and the top of this is going to be this y, or it's going to be some function of fx, then y is c again, since it's going to be in the center there, it's going to just simply be half that height. So we're going to have to do a little algebra while we're there. We're going to have to do some multiplication there, but it's very relatively simple at this particular point in time. And then the same thing. That's an fx squared. So remember, our y is a function of fx. And now I've introduced fx because I need to get up to that height there of that centroid of that particular vertical strip there. And then going back to what looked familiar, what we were doing a week ago was the same sort of thing. Then take that first moment of area and divide it by that area. And the nice thing is note that I calculated area once. I don't need to calculate it twice. It'll be the same for both. So I do that calculation just once. I do those first moment of areas there. That's for a vertical strip. For a horizontal strip, just the opposite. Basically, yc will be equal to y, and your x will then be half of that function. Question?
Why is it half of that function?
Because where we're trying to find is this, we're finding the centroid of this little infinitesimal strip there. Thin this way, but it has height. Okay, since it has height, and we're going to call it a rectangle here, we're going to ignore this little piece there because we are going so small that it's not going to matter. Well, we know the centroid of a rectangle is going to be right in the center. So half the width there, but basically that's so small, there's no half width to worry about. But height there is, because it is this height. Does that make sense? I haven't lost anybody? I see some yawning out there. That's what I'm concerned about. OK, what we'll do is a problem. You've got your handouts there, so we'll just pull it up and talk about it a little bit. I guess you need to see it. OK, so what we're going to do, this is probably something like I say a turbine blade or something like that we're going to have to figure out basically where that centroid is. OK, and of course, basically, they don't give you numbers. They decide to give you an A and a B and that sort of thing. So, but again, we can easily do that. And the other tricky thing is then we've been given our equations with these constants, K1 and K2. And generally, all the exams I've seen and stuff like that, they always make you do that first. So basically, we're going to have to solve for those as a first step. But that's pretty easy because we know the two endpoints. We know it starts at 0, and then they both meet up there at x equal to a and y equal to b. Black pen starting to die. Phew, smelling. Okay, I'm going to write much fatter, I guess, because of this one. Okay, so our first step basically is we're going to get our K1 and our K2. And again, as I said, what we note that we know that particular point, so we can plug that into our equations. And just kind of walk through the steps there. But again, our equations, y1 is equal to k1 x1 squared. We just simply plug in those values, solve for the k1. And this is now what my equation looks like. I solve for my constant there. And I do the same thing for y2. And then that's what that equation will look like. Okay, so what we'll do is we'll get the area of the vertical slices. Now this problem is a little bit different in the fact that when we think about that vertical slice there, we're not running along the bottom there y equals 0 now. We've got a y1 and a y2. So our vertical slice is going to be not only changing in size, but then it's going to also be moving up the y-axis there. Even the bottom will be moving up the y-axis there. But again, something we can deal with. So we're going to do our integration for our area. We'll get that one out of the way first, since that's common to both approaches there, solving for both the x and the y components there. And again, noting we go across from 0 to a, so we've got our limits of integration there, because we're going to be moving along the x direction there. We're taking vertical slices. We'll move it along the x direction there. And what we want to do is then think of our rectangle. But our rectangle is now going to be a little bit different. It's not just the y. It's going to be y1 minus y2. So again, that bottom portion is going to be coming up too. But again, that simply defines a rectangle. Again, when we go to an infinitesimal size there, the curves at the ends don't matter. And we'll be dealing with a rectangle that will be changing in size and moving along up there too. And again, moving along up there is going to be important because, again, our first moment of areas are going to be looking at those moment arms as we go along there. And then all we do is just simply plug in those algebraic values that we solved for there, our y1 and our y2. and then pull out constants. We don't need the b's and the a's floating around if we can pull out. So we note that we've got a b over a squared that we can pull out of both of those. And then note, going through and just simply doing the integration, I got my x squared there will be elevated. The x, we take the exponent, raise it by 1 there, divide by that exponent then. So x to the third over 3. My exponent here is x to the 4. I'll raise that to the 5, divide by the 5. I carry that little a squared around because the b a squared I can pull out. I can't pull it out of that one. I can completely take it out of that one. And then just simply do the integration from my 2 points of integration there, which is 0 and a. Going through the calculation there, and then actually trying to write it down. It'll be 2 over 15 AB. You guys see that? And again, take a look at units. A times B, 2 lengths times each other. That's an area. So we're comfortable in terms of units. I might leave that up. OK, so we'll look at the first moments. In this particular case, we'll do the easy one first. And again, recall, since we're doing vertical strips there, my xc goes to x, basically. It's going to be the integrand across the way there. So the only tricky thing is this is what we did for area, right? This is describing the height of that, the y1 and the y2. And then the only additional thing I got out there now is my moment arm, my x that I'm bringing along there in this particular case for the vertical strip. Again, we want to take out any constants that we can. And then we got to do the multiplication before we do the integration. You could do the integration by parts, but again, I'm not sure you want to spend a whole lot of time doing integration by parts. So we simply do the multiplication before we do the integration. Get our x terms all set up to do the integration. So I'm just simply multiplying x by each piece there. And then I do the integration the same way I did the last one. Very simple. Take those exponents, raise them by 1, take that new exponent and divide by that particular term. Question?
Why does it go to a to the fourth on the bottom?
Oh, thank you. Yeah, I forgot I pulled my a squared out. The magic of integration. OK, and what we find then is we end up with this as 112. And again, note that now it's length cubed, which will make sense because we're going to then divide by that. Okay, the slightly trickier one now is going to be this YC. And again, the situation here is what I want to do is find the center of that rectangle. Now I can't go 1/2 of y1 anymore because my bottom is now coming up with me 2 there. But again, since it's a rectangle, it's pretty simple to find the center of that by just simply adding the y1 and the y2, dividing by 2. And that will find my location of that rectangle based upon my coordinate system that I set up there with my y and my x origin being here. You think it should be minus?
If you did minus, then you'd have to add another y2 to it.
Right, right. You do a minus, but then you'd have to add a 1, and you actually end up with that. Yeah, you get the same thing. Good thinking, though. You're thinking.
I was thinking if you're looking for just the midpoint. Yeah.
Yeah.
That's right.
Yeah, it works out to that. But good thinking. OK, so basically now what we're going to do is that we have to create that y of c. But being careful that I now bring it as a plus sign, and then I also have that new little 1/2 piece that I have to carry along there.
Yeah.
Huh?
I'm getting high off of the fumes, man.
I know, this is.
That was really bad for you.
I was going to say, if I start babbling here, just let me know. I've been inhaling too much. It's the same thing, but it's.
You'll be like, class really went well today.
Yeah, everybody was happy. At least I was. If it's too much, I'll go find another pen. The other one's so light, though. Was it hard to see the other one? I mean, I can go back to the other one if you want. No? OK. You really want to see? Yeah. You're enjoying that. I'm glad they enjoy the class so much. OK, so then again, we're going back to this YCDA. But now we're going to end up with a little messier. We'll pull the 1/2 out. Yes, it will. But here's where, yes, the messy part gets. We got the b over a squared. Sure I get this right. So this is my area, and this is my y of c piece then. So we end up with a much messier piece there because now we're going to have to do the multiplication to get all of my x terms nicely set up for the integration there. But one thing that's kind of nice about that with the plus and the minus, does this look kind of familiar here? Yes, yes. So we actually have a much easier calculation to do there. Since we have a plus and a minus there. And it actually ends up with a much nicer term when we get done with the whole thing. And then just simply doing the integrations like we've done before. Just take those exponents, increase them, And what we find then is that we end up with, again, a simple term, but again, first moment of area, so we've got area times the length, or basically length to the third. Okay, where we're going with that is we want our centroids. And what we do is just simply take that first moment of area that we calculated through the integration there, just like we did with the composites, divide it by the area, and notice that we'll have an a squared there, so that'll be the one thing that's left over. And it makes sense. You need to think about that. The x direction has been given to us, remember, in the a direction, so there's no component of b. We should not expect to see a component of b there. So it's basically telling us in relation to x equal to a, 5/8 over is going to be where the centroid of that particular blade area is. And then the y bar somebody just wishing they could be in this class, I'm sure. And when we get done with this particular piece, then going through the calculations there, what we find out is it's just 1/3 of that height up to find that location. So nothing spectacular. The only thing you're going to be doing is a little bit of integration. Again, get used to it. As engineers, you are going to be doing integrations from time to time. And I will guarantee it will be on the FEEIT exam. Not sure I want to use this thing anymore. Well, our next.
So if we had actual values, it wouldn't be as much as writing.
True. I also think we need to change the name of this book because I'm getting tired. I get thirsty every time I put it up. We're going to skip 5.7. We'll go through that on Tuesday. That's really three-dimensional stuff, and I'm going to save all the three-dimensional stuff for next week. That's about the right percentage for beer, too. Isn't it about 5.8? Depending on the brew. Yeah. So where we're going again with all of this is we spent time finding these centroids and center of gravities. The center of gravities are going to be something, you'll actually have a homework problem on that. But that's something, again, we're going to use. We need to find that weight and location to be able to find out what sort of, be able to use our equilibrium equations. Because, again, equilibrium equations, we need magnitudes and moment arms. OK, now what we're going to find is then we're going to continue this by looking at distributed loads on beams. So we're going to have to then be able to figure out what's going on beams. And the thing about beams is that they're generally not, some of them are designed to carry concentrated loads, but concentrated loads basically aren't the hallmark of beams. When we consider beams, especially if you think of concrete beams, they have weight. They have their own weight to worry about. So what we're going to find is then we're going to have loads that are kind of distributed across that beam. It may be wavy like that. It might be something real simple. But the key thing is then when I think about setting up my equilibrium equation, so I've set up a free body diagram. Pretty simple one there. I'm going to put in how many forces at A?
2.
Forces?
What kind? What, is that a frozen pin?
It's a pin. No, it's a pin. It's not frozen.
Well, one force, but it has 2 components.
Thank you. I'm going to get that through you guys. 2 components, 2 unknowns, 1 force. OK, and then B is a roller. We know that's going to be acting in the y direction. OK, what do I do with this? Can I take this and can I calculate anything with that?
That squiggle?
With that squiggle?
No, I got an equation maybe.
Yeah, think of my equilibrium equation. I'd take a moment about here, right? So I have my moment arm to this one and an unknown force there. I've got a known force here. I should probably have something I could calculate there. But again, I need a moment arm there. What I need is something like that, a concentrated load. So I need that. And then the other piece I need is the x star, which says then x. So I need my magnitude of that force, W, and I need the line of action, or this x star. What I need for my equilibrium equation is x star, which means I need to know the location of that line of action. So what we can do with the process that we went through here in terms of finding centroids is create this equivalent force. Now note, I'm calling it an equivalent force. It's not the force that's really acting on the beam. The force that's acting on the beam is this squiggly thing. It's distributed there. And when you start thinking about mechanics and materials and that sort of thing, and you're going to be looking at bending and stresses here, it's going to be important to know, OK, how much is here, and that sort of thing. So it's distributed across that length there. It doesn't exist as a concentrated load. But we are going to create an equivalent force to be able to then calculate these external forces, again, of that rigid body. And what we'll find is that this magnitude what the magnitude then is going to be this area. The load intensity is this little w. That's supposed to be a big W there. This little w is describing my load intensity. And load intensity is given in terms of force per length. But what we're going to find is then we're going to just have to calculate this area. And we just got done doing that with a centroid, right? I could take this, and if I knew the equation for that, do vertical strips, do a quick calculation. And I've got then some, instead of an area now, I'll have a magnitude. And then the other nice thing that we find is then this line of action has to go through the centroid of the load area. So when I draw this force here, basically what I'm saying is my centroid has to be, my load is acting through that centroid of that area. And the nice thing is basically, the other thing I'll note here too is I only really care about the x direction. Y direction doesn't tell me anything because I'm looking at a force that's going this way. I need the perpendicular moment arm there, which is going to be the x. Okay, so this force area is going to be described in terms of this small omega here, or small w, which is force per length. So it's going to be pounds per foot, pounds per inches, newtons per meter. And then oftentimes we'll be given that load in terms of a function of x. And all we're going to do is the same sort of thing. We're going to take our newfound ability to calculate and integrate. We're just going to love to integrate things right and left here. We'll be able to calculate that area. And we'll also be able to calculate that first moment of area. Just like we did with the centroids through the integration approach there. And we'll do a quick little analogy. So you can see basically that you have your tools in hand here. This equivalent force, this R, is just simply the integration of that load area now. So it's the area of this, but now it's a load area because we have it in terms of load intensity times length. Now note, if this was rectangular, this would be force divided by length times length, which equals force. The two lengths would cancel each other out, which is the same thing that we just got done doing in terms of our centroid. It could be yx or x. And then the centroid piece that we're interested in So basically, it's the same sort of thing that we just got done doing there. The only difference is now instead of substituting a function here, we're going to substitute the function in terms of the load intensity. I'm going to put the pen down now. And what we'll do is we'll kind of walk through this example. We're going to do it two different ways. And you've got most of it, but there'll be a few things that you're going to need to fill out along the way there. But basically, we've been given a beam, and this is typical of a beam. This is what a beam's really designed for, is carrying some sort of a distributed load like so. So we got a distributed load here. Basically, it starts at 2 pounds per foot and ends up at 5 pounds per foot across a 10-foot like there across from A to B. And again, what we're going to be interested in is finding out, OK, what are those support forces? What sort of reactions am I going to see at A and B? So in order to do that, the first thing I need to do is create an equivalent load from that distributed load there. Now, note, I can express my change in length there, noting that our change in load intensity there by a linear function there. So it'll be 2 plus x over 3 over 10, basically, times x. So that's our question. Yeah, are there handouts floating around, or did you not get the handout? Oh. They were hogging him back there. Yeah, it's 3 over 10 times x. Yeah. So that's basically your slope. So you got your slope and your y-intercept there. Everybody got one now? OK, and what we're going to do is approach one. We're going to look at integration, and then we'll look at a much simpler approach when we get going along there. OK, so the next thing is we want to create this equivalent load. So it's just simply, again, integrating that area under the load curve. So I'm just going to simply take that qx, which I've expressed now in terms of that linear function there, plug it in there, do the integration, take it to the various limits there of 0 and 10. And what I end up with is the equivalent magnitude of the load of that distributed load that starts off at 2 and ends up at 5 pounds per foot, basically, will be 35 pounds. So if I were to take that beam and weigh it and see what that distributed load is, basically the distributed load would end up with 35 pounds.
On the right on the bar, is that from 10 to 0?
Yeah, I kind of got wiped out, I guess, in the making the overhead. It's on my sheet right here. So yes, 0 to 10 is your limits of integration there. OK, then the next step is finding that location. And basically, that's that first moment of area again. Now, it'll be about the y-axis, but that's fine, because I'm only interested in x. I've got this load acting vertically down. I don't really care about y because there's nothing horizontal going on there, so I don't need to find that y direction. But I need to find the x direction, and it's just simply going to be x, since I'm taking vertical strips, xc is equal to x, multiplying it times that linear function of the qx that I had there, taking that to the limit, and actually the limits of integration showed up on that one.
Why is it 0.3x squared and now the 0.15
3 over 10 is 1.3 divided by 2 is
Yeah, I raised that to the 3, divided that, which instead of 0.3 now will be 0.1. Yeah. So I did that, and then the 2 also disappeared because that went from x1 to x2, divide by 2. I skipped a step there. But again, when I get done with this, what I get is basically what looks like a moment, right? It's got those moment terms there. It's got a length and some sort of a magnitude there. And then finally, what I can then do is what I'm interested in is then finding the location of this, this line of action. I need to find that line of action there. Simply take the first moment of area, divide it by the area there. And what I find is from the origin, my A point that I've used as x equal to 0, 5.71 feet over, I will find where this equivalent load of 35 pounds is acting. Again, then I think you've got most of the rest of it here. what we're then doing then is then we go back and create our free body diagram. And what we're going to do is we're going to substitute in our A of x and y, the two components of the force there at A, the one direction there, the one force at Vy. And then the thing that I need is that known load. What is its magnitude and where is it acting? And I've now been able to establish that using finding the centroid of that area and finding the area. And I've now located that. And then I can go in and then just simply use the equilibrium equations that I'm so familiar with in terms of two dimensions there. Take moment at A, get rid of those two components from the moment equation there. I can solve for B and then solve for A. Okay, so that's the power of centroids. Everybody got it? I don't want to. Oh, okay. Okay. No. You're not writing them. See, I've got really smelly ones up here. I can write really fast. Okay, everybody comfortable? Now, this was using the approach that we just got done talking about today in terms of integration. Occasionally, you'll have problems like that where there's some weird set of loads on it and stuff like that, and you can describe it as a function or something like that. And you just simply approach it like we did with the integration of centroids. The second method we'll look at here. Sure.
Are you given that equation, or did you have to kind of find that the very first equation, the very top, the q of x, or whatever it is, g of x?
I figured it out. It started at 2, went to 5, and basically it's just a linear function.
So how do you find it without the height? You're just assuming the height is in terms of pounds?
Yeah, well, the height of the load area now is not
So you
y.
found that equation.
Yeah,
Okay.
it's not y, yeah. It's going to be a function of this load intensity, the change in the load intensity, which is now pounds per foot in this particular case.
So
Or
you basically just assume the 2 is a y coordinate, 5 is a y coordinate, and the x is 10, and basically solve for that.
yeah, well, this is what I was given. This is what I was given right here.
Yeah.
And then you can formulate that by just looking at saying, OK, if it's linear, I can formulate the y-intercept is at 2. And this is all in pounds per foot. So the y-intercept is at 2. And then by the time I get to 10, it needs to be 5, which is going to be a slope of 3 over 10 or 0.3. But yes, they'll do that on EIT exams and stuff like that. They'll give you something, they'll give you this, and then you're going to have to figure out that equation if you need it. Now, if they want you to do integration, I mean, obviously, what we're going to see is there's a very easy way to do it with composites. If they do it on the EIT exam, it's going to be some weird curve that you're going to have to do an integration because you're not going to have it in your book. What we're going to look at next here is the simpler approach, and is what we learned on last week, where we can basically break it up now into composite pieces and take advantage of the fact of what we learned there in terms of the discrete formulation of finding that composite, or finding the centroid via two known composites and just simply using a table method. So what we can do is break it up into a rectangular and a triangular area like so, noting that this leg here will be 2, and then the increase of that leg there will, which creates the leg of the triangle then of 3. And then what we're going to do is just look at each of the pieces and try to get the information we have for those and make it actually so you can read it. So the rectangular area there then is just simply pretty simple, 2 times 10. Notice it's in pounds per foot times foot, so basically we'll end up then with an equivalent load. So that rectangular load is equivalent to 20 pounds. And then the location's even simpler because it's in the center of the rectangle there, and it's pretty straightforward. There it's just going to be 5 foot over from either end, actually. And then the next one's the triangle, and again, commit this to memory. It's always going to be 1/3 up from the base or 2/3 from the pointy end. But again, that's one of those ones I'll expect you to know. triangles, rectangles, circles. But the area, again, is just going to be half that of a rectangle. So base times height times 1/2. Basically, what we'll find then is that that triangular area is 15 pounds. And then its location from from that A point there is going to be 2/3 over, again, 2/3 from the pointy end, or 1/3 up from the base, of 6.67. Sir?
Why is it 2/3 and not 1/3 again?
1/3 from the base. I'm measuring from A because I want to do my calculation at A. I'm going to do the same moment calculation I did before. Okay? But it doesn't matter. Yeah, it's always 1/3 from the fat end, basically. But that catches a lot of people because they always think 1/3, and you got to be careful. Where am I measuring from? Question?
Is that the thing that you're telling us to memory, the location of the centroid and the triangle?
Yes. That's what. Put that in your cheat sheet if you're not comfortable with it. But yeah, that one I expect you to know because you're going to use that one for the rest of your engineering careers. OK, and then what we're going to do is solve for the supports using the equivalent areas. But the nice thing about that is then I could resolve this into a single resultant like we did with the other one. But what's an extra force? Just another piece to the moment equation. So I can leave it as two forces. Oh. So my location of my 15-pound is going to be 6.67 over, or 3.33 from here. The location of the rectangular portion there is 20. And then, again, like I say, I could use principle of moments and resolve that into, obviously 20 plus 15 is going to be 35 pounds. So it's the same weight. But I don't need to necessarily do that step. I don't want to do that step because it's just simply two forces in my moment equation. So when I plug it into my moment equation, I just have an extra term. But that's fine. It's easier to solve that than going through solving for the resultant and then going in and just solving for one force there. So when we get to this equivalent approach, we generally want to just leave them as single forces because then we can just simply plug them into the moment equations. There'll just be extra terms in the moment equations, but it saves us a little bit of work there. We don't need to resolve it into one equivalent load in one equivalent location. Got it? There's an enthusiastic yes. Yeah, I think, maybe, possibly. I told you, we need to change the book. Not fair on any of us to be putting up his name. Okay, the next thing we'll look at is getting a new pen. Come on, right. Okay, the next thing we're going to do is then go beyond that a little bit further, and we're going to start looking at fluid forces, again, which is something we're going to have to deal with. And where we're going with this, and again, is we've got fluids acting on a wall or a floor or something like that. We need to find that equivalent force and location of that force to be able to use our statics equations. So we're going to be basically doing the same sort of thing. Let's find the location of that particular equivalent load. Now, fluids are a little messier, however, and we'll talk about that. Okay, so we've got our little built-in pool there. Okay, the first thing is that fluid pressure acts on an area. So when we consider we're going to need to think about this acting on an area there, because it's acting, well, it's wet, it's all over the place, and it'll be acting, so it's not a linear function at this particular point in time, although that's where we're going to be going with it. Another unique feature is that it acts perpendicular to whatever surface it's acting on. So if my pool, for example, had a bevel here, the fluid pressure acting on these various surfaces, on this one it'll be acting on a vertical surface, it'll be acting horizontal. On a horizontal surface, it'll be acting vertical. And then if it's some sort of an angle, it'll be acting perpendicular to that angle. That's the unique feature of it. And that's because it's shearless. It can't carry shear until it's frozen. But basically, because it moves around and that sort of thing, it's allowed to shear freely, basically. The only kind of weight or load it can place on surfaces is going to be perpendicular to it. Question? And then the other thing we need to worry about not X. And I don't know if you've any of you dive or anything like that, but even just diving in a swimming pool, you note that when you get further down, it feels a little more squishy down there. You feel a lot more pressure acting on you. What we'll find is then because it can't carry shear, any of the weight of the water above it is acting on you at that point in time. So the pressure acting here, well, again, let's just draw a picture. If we have a wall and the water level is here, what we'll see is as we go down, that pressure is going to be acting more. There'll be more and more magnitude acting on the wall as you go further down. And the expression for that change in depth, basically, is going to be this equation here. So the pressure is going to change with this equation, P naught is the existing pressure. So if we think about a pool and that sort of thing, there's going to be 14 and a half pounds per square foot at sea level, basically, of existing pressure on it. We get to a new term here. The specific weight, which is going to be expressed as gamma, you'll see that expressed as gamma in most books, which is now weight per volume. So it's not quite density, which is mass per volume question.
The equation for fluid pressure, is it similar to the equation that Vanilla uses to express his definition of pressure?
Yeah, it'll be the same sort of thing. So any of you that have been taking the physics equations and that sort of thing, it's a little bit different here because we're going to be doing it in terms of this other measure of vertical depth, this h. So we're going to be measuring this h, which is going to be, here's my green. Geez, my pens are all dying. This h is a little bit different. So the positive quantity for h is going to be down. So in terms of however I set up my coordinate system, h is always measured from the surface going down, basically. So it's basically, as we can see, it's just collecting the weight of this water as we keep going further and further down, this weight of water that's acting on us, and increases that. Now, we'll simplify this by using just simply the gamma. We'll use what we call the gauge pressure. In most calculations, you'll see simply use the gauge pressure. Again, think about a pool. If I'm considering the atmospheric pressure, well, the atmospheric pressure is also acting on the ground and on these walls if it's an above ground pool and that sort of thing. So I'm not really interested in that. What I'm interested in is the pressure that's going to cause this thing to break, that difference. So we'll be using this gamma h as our tool for calculating pressure. Okay, so where we're going with this is we want to create a force. We want to create a magnitude and some sort of line of action. What we're going to do is do what we've already done. We've done that distributed load on the beam. What we're going to do is with the fluid force, since it's acting on an area, what I'm going to do is pick a fixed width. So I'm going to say 2 feet, 1 foot. And when I take that out of the equation, I take area out of it. Now all of a sudden I got that beam equation that we just did. We've got a beam distributed load acting on that particular beam there. I have it in terms of force per length now. If I pick a fixed width, so I multiply by whatever my fixed width is, I can convert it down to that level and then just simply solve it like I did with the beam load on beams. So if I've got this area here, if I can say I'm looking at 1 foot section of it, I'm going to take the B, multiply times my pressure there, and what I end up with then is a problem that looks like my beam problem. It's now going to be something acting along this line here, and it's going to change linearly with depth. Do this same thing here. But again, depending on the location, it really doesn't matter. Depending on the direction of my surface there, that fluid force is always going to act vertically on that. And whether I'm looking at a vertical section here or one, if it goes down to that same depth, then my same endpoint's going to be different here. Omega times h1. This calculation here, so it should be an h1. Now the loads are distinctly different though too, because when we consider the length of this one versus the length of this one, this is a little bit longer, so it's taking up a little more load there in terms of when we calculate the final load. But again, it looks like a triangular load on a beam. And I think we'll stop there and we'll solve the equivalent plates and curve plates and stuff on Tuesday.